In this video, we're going to hit the basics of logarithms, and remember, when you're looking at a logarithm and you're not sure what goes where, go back to something that you know is true, like 10 to the third equals 1,000, which translates directly to the logarithm log base 10 of 1,000 equals 3. 10 to the third equals 1,000. So putting that to use, let's do 5 to the third equals 125. The base stays the same. So whatever the base of the exponent is, it will be the base of the logarithm. So log base 5 of 125 is 3. 5 to the third is 125. One more. In the opposite direction, 7 to the second is 49. So when you see a logarithm and not sure what goes where, go back to something that you know is true. So let's do some evaluations here, and we can just ask these as questions. 3 to what power is 9? 2. 4 to what power is 1 over 16? If you're unsure, think about the powers of 4. If 4 squared is equal to 16, then 4 to the negative 2 is 1 over 16. Therefore, log base 4 of 1 over 16 is negative 2. 5 to what power? Oh, other way around. 25 to what power is 5? Well, if 5 to the second power is 25, and if we're not trying to get bigger, we're trying to get smaller, it must be a fractional exponent, which is the same thing as a square root. So 25 to the 1/2 is 5. Therefore, 25 to what power is 5? The 1/2 power. Once again, I'll remind you, the 1/2 power is the same thing as the square root. Next, this is log of 1. So if no base is given, it's understood to be a common log, which of course is base 10. So 10 to what power is 1? That would be 10 to the 0 power. And then finally, one last property of logarithms. If your base and your argument are exactly the same thing, the answer is always 1. 7 to the first power is 7, which that is a very basic property of logs. So we can use properties of logs to write expanded logarithms in terms of a single log. Remember, if we're writing a single log, we're only going to write LOG one time. So this is going backwards based on the three properties of logs. The properties of logs are the product property, the quotient property, and the power property. And I usually call the power property the Superman property, which is what we've got right here in this first one. So if I want to undo this 4, 5, and 6, all I need to do is fly them back to their original locations, which were exponents. So this becomes log of x to the 4th plus log of y to the 5th minus log of z to the 6th. Remember, we don't see a base here, and if you don't see a base, once again, it's understood to just be 10, but we just don't have to write it, as that is the common log. So now, I've got a sum and a difference. To undo that sum, these two arguments will be multiplied together. And this is a minus, therefore it will not be multiplied, it will be divided. So, easiest way to remember it is that if it's positive, it stays on the top. If it is negative, it goes to the bottom. Once again, we only wrote LOG one time. Number two, similar situation. First thing we're going to do is Superman these back to being exponents. So we end up with log of x to the 1/2 minus log of y squared minus log of z to the 5th. Once again, if you have a 1/2 power, that is the same thing as a square root. Also a reminder, this guy up front is positive, but both of these guys are negative. Whatever's positive stays on the top. Whatever's negative goes to the bottom. So we end up with log of x to the 1/2, which I will rewrite as the square root of x over minus minus, so y squared, and then z to the 5th. The same properties apply to natural logarithms. Please be reminded that ln means exactly the same thing as log base e. So when you see an ln, it's just a logarithm with a base of e. So if we are going to condense into a single natural logarithm, the same rules that we used on 1 and 2 apply here. If it's positive, it stays on the top. If it's negative, it goes to the bottom. First thing I'm going to do, though, is Superman the 3 back to the b. So ln of a plus ln of b to the 3rd plus 1. Let's also deal with the 1 while we're here. So if ln is log base e, then what can we replace the whole number 1 with? Well, ln of e is 1 because log base e of e is 1. So I am going to replace with a substitution the whole number 1 with simply ln e. Now, take care of the pluses. This will be a full product here. So this is, I'll put it in brackets, a times b cubed times e. ln of a b cubed e. That is how we condense. Finally, just a few log equations to solve here, and we can just use our properties in order to solve these equations. So log base 25 of x equals 5 over 2. So I'm just going to rewrite this as an exponential equation, which you can check out in another video. So now we end up with 25 to the 5/2 equals x. 25 to the 5/2 means the same thing as a fractional exponent. That denominator is going to be the index of our radical. So we end up with the square root of 25 raised to the 5th power. That's what x is equal to. The square root of 25 is 5, and we end up with 5 to the 5th, and 5 to the 5th is 3125. So x equals 3,125 in this particular problem. Number 2, log base 4 of x minus 2 equals 2. Let's go back to an exponential. So 4 to the 2nd equals all of that quantity. 4 squared, of course, is 16. 16 equals x minus 2. And then plus 2, x equals 18 for our final answer. Lastly, number 3 is a good example of the 1-to-1 property in action. We have 1 log base 4 set equal to 1 log base 4. And when two logarithms are set equal to each other, exactly 1 on each side, we can simply cancel the logs and set the arguments equal to each other. Once again, that's only if there's 1. If there's 2, then we're going to need to condense first, then drop the logs. But here we've got log base 4 set equal to log base 4, so that's why we can drop them. This turns into a quadratic equation, which now we can set equal to 0 and solve. So we bring that 6x over. So right now it's not in descending order yet, so let's do that, but let's also make these numbers smaller by dividing everything by 2. 2, of course, is just a number, an integral coefficient, so we can just drop it, and we're left with x squared minus 3x minus 10 equals 0. This is easily factorable, factors of negative 10 that add up to negative 3 are negative 5 and a plus 2. So we end up with two answers here, x equals 5 and x equals negative 2. But let's be certain to take those back to the original equation and be sure they both are logical conclusions. So if I put the positive 5 in, that is simply not a problem. 5 squared is 25, times 2 is 50, 50 minus 20 is 30. And then, of course, 6 times 5 is also 30. But if we put in the negative 2, there is a problem. Because negative 2 squared is 4. 2 times 4 is 8. 8 minus 20 is negative 12. And we cannot take the logarithm of a negative number. We also see that happening over here. So negative 2 gets the boot. Our real best answer is 5.